is this one is a subspace of beta P1. Okay, is a subset of finite index. And contains the orthogonal image. Of pi SL to QP. So that's why, because the candidate we just have is this one, right? Is just D then if we replace this one by this, we can only, so then this is only differed by a module of finite index. Okay, so now we're going back to this D. We want to get a pi of D. So after we get this, we get the p-adic Lagrange correspondence. So what do we have? So we have is D is of dimension 2. So over the field E. So it's a vector space. And we let's say then the determinant of this representation. So determinant D is just corresponding to some alpha D, and the alpha D is just is QP goes to, okay, so it's a character. You take the determinant of the metric, determinant of D, you get a one-dimensional E vector space, but have some action, and this action is by the character. So now we just leave it delta D is just say it's just x times the absolute value of x to the negative one. So absolute value is a p-adic value. So you can take the in, and then you times alpha D. So this is a character. So this is a character from QP star goes to OL. Okay, so this is a character. Now this is the central character we want. So we let this is delta D. We write it as delta. Now we let D check is just D tensor delta D inverse. Then delta D, then this is just this one. It's just the theta dual of this. It's just this theta dual. Is it?
Is this contained in OL, the image of delta D, if you define that x, norm of x, the whole inverse, alpha dx, is this still contained in OL?
You mean this one?
No, the next one.
This one?
Yeah. The inverse.
This is contained in OL.
Right,
but this one is you don't need to. This is in GP star.
X is in QP.
Yeah, x in QP. So x times the absolute value of x is contained in GP star.
X, absolute value x is contained in GP star.
No, x is p to the n times x prime. So x.
Oh, sorry.
Right. Okay. So this. Okay. So this is theta dual of D. Now you get so So now the theorem is this. The theorem is if D is eta phi gamma modulo of dimension 2 over E and irreducible. And then the first one is this one. This is just a, or this is the, we didn't write this, but you remember that we always have delta here. Okay, so and then here the same, the QPZ is contained in this one we defined before. We know we can define this, but we cannot define this because in D nature we don't have the phi is not stable there. So we have this, and then this is stable by G. Okay, so this first one. The second one, we just let pi D is just this. Now, what do we have? This is irreducible object of is this, and you can also prove this is the dual of this. It should be conjugation of this, and then tensor delta D, and one has an exact sequence. So this exact sequence is very much looks like the one about mentioned is dual. So it's and then you get okay. So that's the one, as I mentioned in the beginning of yesterday's course, is about you can decompose this into two parts, and they are almost dual to each other. And here also these are G-stabled, so you actually get decomposition as G representations over G. So that's we get this pi of D. The good thing is D pi of D is just D is just this. Okay, so now from here you can actually, so you get this correspondence. So from here we really finish this p-adic Lagrange correspondence. So in the first one we get from pi we get d of pi, and here from D you get pi of D, and then they can recover each other. So there are several remarks of this. So the first remark is how do we get this kind of construction? So whenever we have a constructions over like a phi gamma modules over E, we almost always, so we start from phi gamma eta torsion. And this is the first step. The second step, you always phi gamma eta OE. And then the last step, you get phi gamma at har E. So the proof of this theorem or the construction of this pi of D is no difference. It's always follows this way. So you can see, so from the proof, this reduction module P is very natural. It's already there because you actually start from reduction module P. So that's why I mentioned yesterday, say this reduction module P is very good in here. So that's why the case. So because it's very naturally compatible because you start from there. Mm-hmm.
So the first error comes from just by taking inverse limit with caution.
Yes.
And what about the second step?
Tensor L.
Oh,
Tensor, yes. Tensor, so here is tensor ipsilon, tensor E. Yeah. Okay. So it's just tensor product. First one is project limit. Okay. So this is this remark. And the second remark we want to have is this. Recall here is we have this, and we recall we have another this kind of similar thing. We get say C0 GP L dual goes to C0 GP L goes to 0. So this E is the dual, the extension of one binary space by its dual. And this is almost the phenomena is also like this. Is a dual by another, is something by its dual. So, but we know this. We also know we can construct all these things. This we don't have to choose this delta equals delta D. So here we use delta D. But this one we can construct for all D. So the conjecture is only this D we have this kind of decomposition is fixed by you have a G module here structure. For all other delta, this is not true. Okay, so one thing is this. So this is delta D is the only character. So the conjecture is that delta D is the only character such that the component of the component of the extensions of this extension or any kind of extension is stable, are stable by G. But this extension should satisfy similar property, is dual and to itself. Okay, so because we have all D but all delta, well here the theorem is just one delta D, only works for one delta D. Okay, so this is the second remark. So the third remark, what do we have here? The stability. So this stability of this. We use the analytic method, and a very complicated analytic method. So the question is, are there any direct proof? So is there any direct proof using 3 gamma modules. So this is not true. This is not no. I don't know if it's true or not, because here is extending all these kind of analytical methods. Okay. So this is the third one, and the first one is this. The first one I want to talk about is about this kind of analytic proof, so works in families. So that means you can actually choose D is et al. So here is D is et al. Over E. So you can choose D et al. Over some S tensor E. And then delta is from here to here. Then you can get this one, delta P1. At each point, you can use an S representation. And we also interpolating. So ds delta S and P1 for S in spec X. So that works in families. Okay. So this is because of the analytic method. Okay. Because you have this analytic method, you have this. So that's a remark for this theorem. So now the rest we need to talk a little bit about something called locally analytic vector and locally algebraic vector. And this is corresponding to the classical Lalan's program. So locally analytic vector. So now is so with a V is contained in pi. So pi is just a unitary admissible. It's just satisfying all this nice property. It's locally analytic if this G goes to mu GV. So mu is in the dual. So in this bracket is locally analytic. Function over G. Okay, so if we take all this kind of vectors, then we get a pi an. So it's just V locally analytic. This one is stable by G. Then the good thing is this is not zero. It's not empty. So there exists something here. And then the theorem here is this. This is actually well connected to the one to the notation we had, see, we already get this. We always use D natural, D sharp, but we didn't use this D dagger yet. So it's actually we have this. This one is isomorphic. So it's just the image of the dagger. Now this is over-convergent element. Now here we have, before that we don't have this over-convergent element. So now we go back to over-convergent element. So this is just an over-convergent element in p-adic. Yes?
Can you briefly just mention what do you mean by locally analytic function of G?
Okay, locally analytic function means, say for example, locally analytic function over ZP. For our GL2QP is the same. Okay, it's just saying is near a neighborhood, open neighborhood, you can have a Taylor expansion. Yes. So you can write it into
In the sense of p-adic.
Yes, okay. In power theories. Yes. So that's analytic usually is like this. So locally analytics just means everywhere exist all this thing. Yeah.
Because G is a group that you can have a...
But G is GL2QP. You have structure here. You have like open sets like GL2QP. You have I.
Group. So if you have one point at the local analytic, then you can. Is it impossible to
No, so this function is not a group homomorphism.
Oh, sure.
Yeah. So you just want to in this topological space. Okay. Yeah. So this one is just this. Okay. And also this one is a. So what is this one? You can define it because it's the same thing. Is just all this Z1, Z2, Z1, Z2 is contained in the dagger and satisfy some conditions. Okay, is stable by G. So that means if you want to identify the local analytic elements, vectors, is really connected to the over-convergent elements. And also, this action, the action of G, extends to this so-called D-rigid. We know we always have this. You have E, you have including E dagger. So this is overfill, and then this is included in the Roba ring. So this is Roba ring. So this is a field of over-convergent. And then the correspondingly you have here D, and then here you have D dagger. So all the vector space, because this field is a vector space. And then here you have D rigid. So it's D rigid. So from here to here you just take its completion. From completion to R you get this. So again, so you from D dagger to D rigid you also take completion. So you take a completion by continuity. And then you have this. One has an exact sequence. What kind of exact sequence? It's just 0 goes to pi of d, the dual, and then tensor delta d, and then take to the d digit, and then go pi of d. An goes to 0. Okay. So this one, the proof of this, use the expansion to prove of this stable by G. You need to check this is stable by this W element. W is the 0, 1, 1, 0 matrix. And then to prove this, okay, the remark. So the proof use this module. Which module is the C of D? It's phi minus 1 D psi equals 1. We used this module. And this module is very central in the Iwasawa theory. So in all this local p-adic representation, this is central to the one to prove the result of Hale, actually to prove the local theta duality, all this. And this what Fontaine called is the core of phi gamma modules of D. Okay, it's just the core of D. So this is for locally analytic vector, you use this. And then also for locally, so the next section is about locally and algebraic vector. You need to use this, especially to the theorem of Iwasawa theory and the explicit reciprocity law. So this is an p-adic classical. So you can say p-adic and the classical Lagrange correspondence. So here, so what is V is contained in pi is locally algebraic. So you just change the definition here. It's locally analytic means this function is locally analytic. So if locally algebraic means this G goes to mu is locally polynomial. For all mu. So if it's a polynomial, here is a power series, and here is a polynomial. And then what kind of polynomial? So it's in term of A, B, C, D, and AD minus BC. So it's a polynomial of these variables. Otherwise, it's not a polynomial, you know. Okay, so we call it like this. So, the thing is, in many times, this pi algebraic is just 0 in most cases. So, this is not like this. This is not 0. Okay? So, here in most cases, it's 0. But, so, the theorem is this. The theorem is pi d is not 0 if and only if d is belong. So this is a terminology in p-adic Hodge series, so I didn't have time to tell you what is the RAM representation, but yeah, this long work with Hodge-Tate weight, with distinct Hodge-Tate weight. And more say A less than B, because this is two-dimensional. So there are only two Hodge-Tate weight. So when I say one is A, the other is B. Then, and what is p-adic algebraic in this case? In this case, p-adic algebraic, you can decompose it into p-adic locally constant, and then tensor part of symmetric power of b minus a minus 1, and tensor determinant to the power a. Okay? So this symmetric power is over QP cos QP, okay, plus QP, and then you take this P minus A minus 1 symmetric power of this, and then you get the representation. So this is locally, so p-adic LC is locally constant. This is locally constant admissible representation of G. So this is locally constant admissible. Okay. Of G.
One more question.
Yes?
I missed the first few sections of the structure. So what do you mean by the locally algebraic definition?
So locally algebraic means this.
Just the
Locally is a polynomial.
this definition.
Yeah, this is just a definition.
Why algebraic? Then is this the set of all locally algebraic elements?
Yes. Sorry, I didn't write down here. Yes, it's just a set of all locally algebraic vectors. Okay. So this is definition. If. Okay. So this is the definition. So usually in most cases this is 0. Now in this case, if D is the RAM, it's just the corresponding representation is the RAM, and the Hodge-Tate weight is A and B. The Hodge-Tate weight is just the valuation of the eigenvalues of the Frobenius. Is just Hodge-Tate weight. So the C is the one thing is not. So the one. So implies so-called potentially semi-stable. So this is a big theorem. It's just using this overconvergent element by Bourget and others. He proved this theorem. So if a representation is the RAM, then it's potentially semi-stable. Certainly, the other way, this is equivalent. Okay. Before that, this is called so-called monogamy conjecture, I think. And now it's proved. So it's potentially semi-stable, and then potentially semi-stable. So this is corresponding to some module is called phi n GQP module. So this is always 1-1 correspondence. So it's D, we know is 1-1 corresponding to V. But if this is the RAM or potentially semi-stable, the corresponding to phi is still Frobenius. M here means Newton, or let's see, say nilpotent. Is some nilpotent operator, and GQP is just GK. So this all this you can see in my future book, but is explained there. It's already there, I think. So then you can get some called DPST. So the thing is, now for this DPST, you can extend to a WQP module. So representation. So WQP is the validating group of QP. Okay. Now the classical. So this is a so-called classical Lagrange correspondence is, for this one you have a representation over G. So here is a representation over GQ over WQP. So this is validating group. So the classical local Lagrange you corresponding to some LL DPST. So this is classical Lagrange. Okay. So the theorem is this. In this condition, this pi d LC locally constant. This is nothing but this. Okay. So that's the third point about this p-adic local Lagrange correspondence. Say it contains the classical one, and how do they contain it? Is just using this. Okay. So this is this is the one so-called p-adic and the classical correspondence. And then the last thing I want to say is, and still I didn't have time to read this. So the last thing is what I really have interest in, but I don't have time to finish. It's about these locally algebraic vectors and the relationship with Iwasawa theory. So this last one is Iwasawa theory. And locally algebraic vectors. So in this case, so we recall what we have in the Iwasawa algebra. So this is the Iwasawa algebra, right? OLT. If you really are familiar with ZP, you just replace this OL by ZP. This is the Iwasawa algebra. And we have V is GQP. And then corresponding to DV. Okay. And we also have pi V by the correspondence. So dV is phi gamma module, pi v is representation of G. So we also have d psi equals 1. So we actually have from here we have this. This is just this one. If we have a correspondence like this, mu P001 mu equals mu. We can actually have a map from here to here. This map is just mu. It goes to this beta ZP mu. Then this is isomorphism. This is an isomorphism. But then the one I said, this one is very important in Iwasawa theory. What is this? So the Iwasawa theory, we have this H1IW GQP So we say Fn is QP mu Pn. Okay. So we know this is, what is this? This is just say the projective limit of H1 GFN. Sorry, we just say V. V. But this will correspond to, if you take the limit, exchange the limit and here, you actually get this is using the Shapiro's lemma. Using Shapiro's lemma, you can get this is nothing but this GQP and then lambda tensor product V. Okay, so in many cases, if V is good, like for example, is crystalline or semi-stable, and then you can, this is can be described in terms of measures. So this is one side. So you get this is really you get measures and distributions over ZP. On the other hand, because of the result of Fontaine and Hale, and you can get this. This is actually proved by Fontaine, but he never published. This is just the dV per psi equals 1. So using the result of using the Galois cohomology I described there. So this, now you see the distributions and the measures. This part I didn't talk, but in my notes, you know, distributions and measures, you get what? You get p-adic L functions. Okay, so the thing is here, if you have an element here, so that means if you have some element here, say from going from global objects, so here is very local, but sometimes in cyclotomic fields you have some global units and satisfy some properties, and say, so if you get a restriction to the local ones, so you get an element here, and then you will get p-adic L functions. So that's the thing of why this one is important to the Iwasawa theory and the p-adic L function. Is one of these. Okay. So yes.
Trivial direction to show the equality dV. Carbon in general trivially contains in bottom of
You mean this one?
Yeah.
Contained in this one?
Yeah. So the difficult thing is the other direction.
Well, this identity is easy. Anyway, it's very easy to prove. So this identity is nothing. We just need to know this one. 0 goes dV. So this is say is C phi gamma, but if you for this is Fn, you get gamma n. Okay, so you get like gamma n plus 1. So you have a morphism of complexes. Okay, and then if you take the cohomology, it's just this projection. It's just this projection is just constriction max, and induced by this cohomology of complexes. And if you take the projected limit, then you get the first projected limit, you get 0, The second one you just get dv. The last one you get dv. You get 0, and then the map become d psi minus 1. Okay, so the cohomology here is just dv psi equals 1. Here is the dv over psi minus 1. Yeah. So if you just want to prove this, yeah, that's easy. Okay, but how to use this? For example, that just v equals dp1 is not trivial. So the thing is you want to use it. So find the element here and to find the meaning in number theory, for example. So we can pick, there are many elements here, right? Some elements are very useful, some may be not so interesting. Yeah. Okay. So then this is the trick is there is this one CD, as I just say, is the psi equals 1. But this one is will be important to study, and then I don't think I can continue very deep because this one the later part I didn't read more carefully. So, but anyway, you will have some pairing here. So you have a CD here, you have some pairing, and actually you also have this pairing. You can also have this pairing, you have some duality, and this duality you can go through lambda. So here again, so this is a pairing. And this pairing, you can induce some pairing here. This goes to lambda. And this pairing is perfect pairing. Perfect. Okay. So if you get this kind of perfect pairing, and you can also get some other thing, you will get you will get something like, so I just make some result you will get from here, from this direction. You will get this bearing here, the reciprocity law of p-adic L function. You know, she has a book. First is in French, and now it's translated in English about this universal theory and p-adic L function. So you can get this, and also like this reciprocity law of her, which was proved by, I think, first proved by Comets, and the conjecture is by her. So, and also you have some called reciprocity law of Kato. Okay, so and this maybe called explicit reciprocity law of Kato, and among any other things. I heard, I think the current research Comets is concentrating on is also on this, about this locally algebraic vectors. So that's the one probably will be more interested in a few years. So I think I'll just stop here. Yeah, thank you.